Most of the big CFD code you'll ever touch, Fluent, OpenFOAM, Star-CCM+, are built on one method. And it isn't the finite differences you might expect, it's the finite volume method. The reason it won comes down to one almost stubborn property: it refuses to lose track of mass. Whatever flows in, flows back out, or piles up, it never just quietly vanishes. Here's how it pulls that off. Finite differences think in points. Lay down a grid, approximate the derivative at each point. The finite volume method thinks in boxes. You chop the domain into little cells called control volumes. And instead of asking what the derivative is right here, you ask something more physical. How much stuff is inside this box, and how does that amount change? Each cell becomes a tiny bank account for mass or momentum or energy. And like any account, the balance moves only when something crosses the boundary. So zoom into one cell. It has faces, 4 of them in 2 dimensions, 6 in 3. Across every face, the fluid carries stuff in or out, and that crossing rate is what we call a flux. The rule is pure bookkeeping. The rate the quantity inside changes equals everything flowing in across the faces, minus everything flowing out, plus anything created inside. That's the whole thing. It's the conservation law again, written not as an abstract derivative, but as a balance sheet for a finite box. Now here's the part that makes the method work. Take 2 cells sitting side by side. They share a face. The flux leaving the left cell through that face is the exact same number as the flux entering the right cell, because it's one face, one flux, computed once and handed to both. So whatever the left cell loses, the right cell gains. Nothing is created or destroyed at that interface. Now line up a whole row of cells and add up all their fluxes. Every interior face shows up twice, with opposite signs, and they cancel in pairs. The only fluxes left standing are the ones at the outer edges of the domain. So the total mass across the whole grid can change only through the outer boundary. Exactly, to machine precision on any mesh, however coarse or lopsided. The method conserves by construction. You don't hope for it. The arithmetic guarantees it. This is the contrast with finite differences. They approximate the derivative directly at each point, which is clean, simple, and on a smooth grid often very accurate. But nothing in that approximation forces the books to balance. On a coarse or distorted mesh, a finite difference scheme can quietly manufacture or destroy a little mass at every step, and that error piles up. The finite volume method never asks the derivative to behave. It integrates the law over each box and balances the fluxes, so conservation holds no matter how good or bad the mesh is. In engineering, a leaking solver is worse than a slightly inaccurate one, so that guarantee is the whole game. To turn this into numbers, the solver needs the flux on each face. And there's the catch. It stores values at cell centers, but it needs the value at the face in between. So it interpolates, and exactly how you interpolate is a topic of its own. The convection schemes, upwind versus central, that we'll come back to in another video. Once every phase flux is written in terms of the neighboring cell values, each cell's balance becomes a single equation. Stack all of them together, and you get the giant linear system a CFD solver actually grinds through. The same arithmetic on cells idea from the very beginning. There's a second reason it dominates. Because all the method ever needs is the flux through a face, it doesn't care what shape the cell is. Triangles, tetrahedra, lopsided polyhedra, as long as the cell has faces, you can balance fluxes across them. So you can wrap a messy, unstructured mesh around a turbine blade or an artery, and the finite volume method still conserves exactly. Finite differences want a structured grid lined up with the axes, which is hopeless for a real engineering shape. Flexibility and guaranteed conservation together. That's the pairing that put it inside nearly every solver. So the finite volume method is one idea. Don't approximate derivatives at points. Balance the fluxes across the faces of little boxes. Because neighboring cells share a face and a single flux, what one loses another gains, and the whole domain conserves mass, momentum, and energy exactly on any mesh you hand it. That's the quiet, stubborn property sitting underneath nearly every CFD code in the world. That's all for this video.